Sorry for issues to do with network that they have disconnected our phase one of section 2. It is my hope that this one we can make through. So, welcome back. Still reminding you of this good online program where you need to have us on board. We help you a kid. We help you as a student. We keep you busy over the December holiday. So you can keep in touch with the number that you can see on the screen so that you can enroll. You can enroll to this program. Thank you so much and welcome so that we may continue with the physics paper 2, Maranda. So I left somewhere where I said that we have the neutral and we have the earthing. So this was the diagram. For those who are still with us, that was the diagram. So we said that you need to have some supportive arguments. The earthing is connected to the Kcse. So earthing is always connected to the Kcse. So that in case of any stray charges, they are disposed of or they are discharged immediately. We have our next question. And this one, we are told that the figure 7 shows the apparatus used to produce X-rays. The apparatus used to produce X-rays. Then we are having the diagram there. Then you are told name parts marked A and B. The parts marked A and B. So you can see A, it is C-shaped. It is C-shaped. This is now A, is C-shaped. There is a reason for why it is being in that manner. Then we have part B. We can see we have a metal target that is attached to part B. So we can start with B because we have a clue. This is where we have the metal target, which stops the beam of electrons. So B becomes the anode, whereas A is the cathode. So now, briefly explain how X-rays are produced in this case. So once they are produced, we have the heating current at the cathode. Electrons will be ejected. Then they will be accelerated towards the metal target by the potential difference. Then once they hit the metal target, they will be turned now to the X-rays. Therefore, I can give the explanation. When the current flows through, flows through, the filaments, in the cathode, electrons are produced by a process called thermionic So these electrons are accelerated towards the metal target. Where they are suddenly stops. Producing X-rays. So that is it. That is how they are produced. That is how they are produced. An X-ray tube is operating at an anode of 5 kilovolts and a current of 10 milliamperes. Explain how the intensity of the X-rays from such a tube may be increased. So this is supposed to be just a statement that you're supposed to give out. Therefore, intensity means the quantity. Intensity. So intensity means the quantity must be I. The quantity must be I. So for the quantity to increase, then where do we touch? You only touch at the 18 current. So the intensity can be increased by increasing the 18 current. And if now you want to look at the penetrating power, which is the next question, this one we consider the quality. And the quality of X-rays, whatever can be adjusted, is only the accelerating potential difference. So increase the accelerating potential difference. We can move to the next part. Calculate the number of electrons hitting the anode per second. Remember, in our question, we were told that it is operating at 5 kilovolts and a current of 10 milliamperes. So now you are asked, calculate the number of electrons hitting the anode per second. From this, let's calculate the charge first. You know that charge is given by current times time. So our current in this case is 10 milliamperes, and this is equivalent to 10 times 10 raised to power negative 3 amperes. So now our T in this case, because it is per second, as we say 1 second. Therefore, we substitute. So our Q will be the same as 10 times 10 raised to power negative 3 times 1. And this gives us 0.01 coulombs. 0.01 coulombs. From here, you need to calculate the number of electrons, and this one, we say that the number of electrons is given by the charge over the electron charge. This is electron charge. So we say it is Q of 0.01 divided by 1.6 times 10 raised to power negative 19. And this is going to lead us to a number of 6.25 times 10 raised to power negative 16. So the number of electrons will be supposed to be a positive number, sorry. Electrons, like that. Ambassador, thank you for following. This is the place to be. Determine the velocity with the electrons, velocity with which the electrons strike the target. Then you are told take the electron charge to be 1.6 times 10 raised to power negative 19, and the mass of electron to be 9.1 times 10 raised to power negative 31 kilograms. So now in this case, you need to understand how do we get the kinetic energy. So we know that kinetic energy is given by half the mass of the electron times velocity squared. We still have another method of getting kinetic energy where we say it is given in electron volts. So we can say EV is the same as half MEV squared. We have the electron charge. Do we have the voltage or the potential difference? Yes. So I can say 1.6 times 10 raised to power negative 19 times our V here. We said it is 5 kilovolts from the previous question, this one. So it is 5 times 10 raised to power 3 volts. And this is supposed to be equated to half the mass of the electron, which is 9.1 times 10 raised to power negative 31 times V squared. So our V squared, making it to be the subject of the formula. So our V squared will be divided through by 9.1 times 10 raised to power negative 31 and you multiply through by 2. So it will be 1.6 times 10 raised to power negative 19 times 5 times 10 raised to power 3 divided by, sorry, we multiply by these 2 times 2 divided by 9.1 times 10 raised to power negative 31. And these will result as to V squared is equals to 1.758 times 10 raised to power 25. So our V now becomes the square root of this one, where we get to 4.193 times 10 raised to power 7 meters per second. So you get the square root of this. Get the square root. Thank you all for joining. What property of lead makes it suitable for use as shielding material? Remember, this one is used especially in places where we have so much radiation, and the reason is because of its density. So it has a very high density. It has high density, hence absorbs stray X-rays. Hence absorbs that is stray X-rays. I'm here to still remind you of our December online program. Our December online program, where you are invited. You are highly invited. You are highly invited. This is Ascending Grace Online School. Shall be having Google Meet classes, and thereafter we engage lively in the YouTube. So we are having a program which we are calling December holiday program. It is of 5 weeks. It is running from 11th November to 12th December. We are operating within mathematics and the sciences. Elevate your grades, elevate your future. You can inquire through the number you can see on your screen. Can inquire through that number, 0757019011. So tell a friend and feel so much welcome. So now we can continue with our questions. In a modern cathode array oscilloscope, are set and deflection plates called X and Y plates and time base. So you ask, what is the function of the time base? The function of this one is to vary, or you can say it varies the voltage on and the X plates on the X plates for horizontal deflection. Of the spots on the screen. What could be the trace seen when the time base is switched off and a DC voltage is applied to the Y plates. So we expect the motion to be up and down, and this will be that the spot will move up and down. The spots will move up and down. Then an AC voltage is applied to the Y plates. So still, the issue that we are looking at is the type of voltage that is being applied. So the DC will be moving up and down, but the AC one, because of its high frequency, then we expect to see not only a spot but something that is continuous. So a vertical line will be seen moving, will be seen on the screen. Or if we talk of the spots, then it will be moving at very high speed. Spots will be or will move up and down continuously. So that is the difference between the AC and the DC voltage when applied to the Y plates. Remember the Y plates? We are looking or considering the vertical deflection. Set the Lenz's law of electromagnetic induction. It says that this is a law that is difficult to many. The direction of induced EMF is such that the induced current which it causes to flow produces magnetic effects that opposes the change. Producing it. So that is the Lenz's law. Give us a like. You may comment on the live chat section as we continue. So this is the Lenz's law. But most of the people don't know how to state it, but they know how to apply it. Therefore, we are having as part B, which will be a coil is moved quickly away from the end of a stationary magnet Y, and the current is flowing as shown by this figure. Then I want us to understand that here it is the coil that is moving, but in class we are told when the magnet is moving. So we do expect some changes here. Therefore, this coil is moving in this direction. This is Y. It is stationary. Now, the polarity of Y will become a north pole. Then we need to support our argument. So this one becomes our north pole. Let's back on our feet. Ask ourselves, why is it north pole? If you look at that diagram very well, naturally, if you engulf your fingers on that coil, if you engulf your fingers on that coil, uh, then you will see that this further end, this one, will be telling us to be a north pole. Will be telling us to be a north pole. If you look at it clearly. So meaning that the one on the left, this one will become south pole. Will become south pole. Unlike the other one, where we have the magnet moving, you need to create a repulsive force. In this case, we expect to get an attractive force. So if this is south, then automatically our Y becomes north pole. But suppose now it could be the magnet that is moving like this. If it is the magnet that is in motion, and the coil is designed the way you can see on the screen, then we expect naturally to have this end to be north pole, and this one to be south pole. But because it is the magnet that is in motion and applying this Lenz's law, we expect a repulsive force. So we expect this Y section to be south pole so that it can be repelled away by the south pole of that end of the coil. That is the difference. So we can write it. When the magnet is in motion, a repulsive force is considered. And when the coil is in motion, attractive force is considered. So that is something that you are supposed to put into your mind the moment you are asked about this. Our next question is, state the essential condition for the EMF to be induced in a conductor. There must be relative motion. Relative motion. Between the fields and the conductor. In short, we need to have a change in flux linkage. That is what it is supposed to be. To my viewers, we are still reminding you of this program. Just a second, you see this program. Call that number you can see on the screen so that you may get in touch with us. 0757 01 9011. So now we can move to part D, which says a student wound two coils on a cardboard tube as shown. So this is the tube, and this is the windings of the coil. Explain what happens when the switch is closed. Explain what happens when the switch is closed. Aha. So this one, we do expect some mutual induction. And it has been awarded 3 marks. So we expect the flow of current in the first coil to create some magnetic fields, and these magnetic fields will create some induced EMF or current in the second coil. Therefore, I can say the current in the first coil build up to maximum. Magnetic fields produce cuts across the second coil. So a change in magnetic flux linkage is created in the coil, inducing an EMF and the current in the second coil cause a deflection. On the galvanometer. On the galvanometer. What would happen if the experiment were repeated, but this time soft iron core is put in the cardboard tube? Remember, if soft iron core is used, then it is going to improve the flux linkage, the rate at which the magnetism that is created is going to link up with the second coil. Therefore, we do expect a greater deflection. So you can say a greater deflection is observed since it will have greater change in flux, change in magnetic field. Due to his magnetization of the soft ion core. All right. So now, after so many explanation questions, now we can get into questions. The figure below shows a transformer used to step down power for use by an electrical appliance. So you can see the input is of 240 volts and the output is of 12 volts. Then you are told calculate power inputs. So our power input is the same as the voltage times I. And which voltage is this? It is of 240 times 0.1. And this is going to give us 24 watts. The second part, assuming there is no power losses in the transformer, calculate the reading on the output part. So allow me bring this working here. So assuming that there is no power loss, then we say the power input will be the same as the power output. So P in will be the same as P out. So our 24 watts will be the same as the voltage of 12 volts times the output current. So our I, which is subject the formula, will be 24 divided by 12, giving us 2 amperes. Giving us 2 amperes. Is it possible we say this was a V1, I1, and this was V2, I2? So that we say I2 is equals to 2 amperes. I2 is equals to 2 amperes. What would be the output power if the transformer had been 80% efficient? If the power output would be 80% efficient, we know that efficiency is given by power outputs over power inputs. Then we express it in percentage form. So our 80 will be the same as power out divided by our power input, which is of 24. Then we multiply by 100. And therefore, this gives P out as 80 times 24 divided by 100. And this is going to give us from calculation, it will be 19.2 watts. It will be 19.2 watts. Aha. Now, can I have the next part? Yes, now we can move on to question 17. Uh, but before we move to question 17, there is somewhere where we have skipped. So this working is supposed to be for Roman 3. So this is Roman 3. So now Roman 4. Roman 4. The working for this one is here, Roman 4. What would be the reading on the ammeter on the output parts and the transformer being 80% efficient? So since we have got the power output as 19.2 watts, then our voltage there we can see from the diagram is 12 volts. Then our current will be what? So our current will be the same as 19.2 divided by 12. So this one leads us to 1.6 amperes. 1.6 amperes. We have, let me check if it is our last question. Our second last question, which is reading the figure, shows two speakers connected to audio frequency generator. And then, why are the speakers connected to the same audio frequency? So we want to test the issues to do with interference of waves, and these one, we want them to produce coherent sound wave. So it is going to be a coherent sound wave source. So because they are from the same frequency, then that is what it will be actually. A source of coherent sound. Set and explain the observation made when the observer is moving along the path PQ, up and down. Since you are moving along PQ, we expect the alteration of constructive and destructive interference. That is and loud and soft sound to be heard. Therefore, I think this question we can respond it here. So alternates, loud and soft sounds is at loud sounds is as a result of constructive interference while softs is as a result of destructive interference. State of observation made if the signal of the generator is increased. If the signal generator was increased. So the distance or the intervals of the loud and the soft sound will be reduced. So you can say the separation or the intervals of loud and soft sounds is reduced. Explain the observation made along AB, these parts. So we expect a constant sound. Because it is at the center, then we expect constructive interference. So a constant loud sound is at state what would be observed if the cathode ray oscilloscope is moved along PQ. This cathode ray oscilloscope is like testing what type of wave will be formed. So there will be formation of a transverse wave. Transverse wave. A transverse wave is the one in which the particle causing the displacement moves perpendicular to the wave direction. That is where the sound lies. Our last question for those who don't like explanation question, at least we can have some more part of explanation. But nowadays, because it is known that it is easier for you to do calculation, then you forget about the the explanation question. That is why most of the current papers that you see are giving a lot of theory explanation work because they understand that students have neglected the explanatory questions. They are committed to calculative questions. Still, I'm reminding you of this program, Ascending Grace Online School, the place to be. 5 weeks program come December. Kick in from 11th November to 12th December. Enroll, enroll through the number on the screen, which is 0757 01 90 11. So now we can move to the last question. Define the term refractive index. Then it is defined as is the ratio of the sine of incident angle to the sine of the refracted angle. Is the ratio of the sine of incident angle to the sine of the refractive angle. Or we can use the velocity, or we divide in terms of velocity. Ratio of velocity of light through vacuum to velocity of light through a medium. Through a medium. State two conditions necessary for total internal reflection to occur. Conditions necessary for total internal reflection to occur. They are always two. Then the first one is that light must be traveling from an optically denser, or you could say from a denser medium to a less dense medium. Then the second condition is that the angle of incidence must, we have a certain part that I've skipped. The angle of incidence in the optically dense medium are mixing up the points. The angle of incidence must be greater than the critical angle. Than the critical angle. Then we are asked, you define or you explain what you understand by the term critical angle is applied in optics. So, is the angle the optically, the network is backfiring again, but it is our hope that we continue till we finish clearly. For which the angle of refraction in the less dense medium is 90 degrees. Then we have the last bit where we have an application question. You can look at the diagram clearly that we are having an incident ray on side AC. Then it is perpendicular, meaning that it is going to penetrate through and deviated. And you are told, given that the critical angle for the glass is 39, scale the diagram, the path of the ray through the prism. So we are going to draw it. Like that. So if this is 40 and this is 90, it means that this one is 50. So if you draw an imaginary normal, then we'll say that our incident angle on the side of AB will be 40 degrees. If you look at 40 degrees as our incident angle, it is greater than 39, which is our critical angle. So 40 degrees is greater than our critical angle C, which have been given or mentioned here. So we do expect that a total internal reflection to occur. The angle of incidence must be greater than the critical angle for total internal reflection to occur. So this one will be taken as to total internal reflection. So it will not be refraction, but total internal reflection. So we have to draw our reflected angle. Like this. So this becomes also 40, and because this is 90, it will come out undeviated like that. It will come out undeviated. But now, suppose the incident angle along AB be 37 degrees. So in this case, we expect refraction to occur. That marks the end of these Maranda mock examinations of 2025. Kindly remember to share this work with a friend. Growing together is a good thing. May it be of help, may it be of substance unto you. Still, I'm going to share this program, which is the December online program, the Google Meet classes. Welcome to Ascending Grades, where you're going to meet a team of experts in sciences and in mathematics. We are here to elevate your grades, and this shall have a positive impact on your future. Shift the focus towards sciences and mathematics. Bye bye.